Welcome to the Parallel Computing Unleashing the Potential of Parallelism. Before we dive in, let's first understand the traditional approach. In sequential computing, the computer executes each operation of a program in order, one at a time. Sequential computing is the standard programming model where tasks are performed sequentially without concurrent execution. While this model is straightforward and easy to understand, it has its limitation, and especially when dealing with computational intensive tasks. Consider a common scenario, detecting cats in a collection of images. Let's examine a simple sequential program designed to process images and count the number of images containing cats. As we can see, the program iterates through a list of images, calling a function to detect cats in each images, and updating a counter accordingly. Each operation is executed sequentially, one after the other. Now, let's analyze the sequential execution of our cat detection program. This analysis reveals the sequential nature of the program, where each operation waits for its predecessor to complete proceeding. While this approach is intuitive, it may result in suboptimal performance, especially for large data sets or complex computations. Sequential computing, while conceptual simple, has inherent limitations that hinder its scalability and efficiency. Since this is a single threaded execution, it only one operation can be executed at a time, leading to potential bottlenecks and idle processor cycles. Second, operations are processed sequentially, which is why it's linear progression, and resulting in longer execution time for computational intensive tasks. And last, it is limited resource utilization because the full computational power of multi-core processors remains untapped as core operate independently without coordination. This limitation underscored the need for alternative approaches to computation, such as parallel computing, to be discussed later on, to overcome performance per bottleneck and accelerate computation. Now, let's enter deep dive into the world of parallel computing, a paradigm shift that revolutionized computation by enabling multiple operations to be executed simultaneously. Unlike sequential computing, where tasks are proceed one after the other, parallel computing distributes computational tasks across multiple processors, harnessing the power of concurrency to achieve remarkable performance gains. Upon revisiting the program, we can identify operations that don't need to happen sequentially, especially the operation inside the loop that calls the detect cat function can be parallelized as each call is independent of the others. To parallelize the program, we instruct the computer to execute the detect cat function calls in parallel. Now let's assess the performance of our parallelized program. The non-parallelized program, the non-parallelized operations remains unchanged, while the parallelized operations will now execute concurrently. Behold the timeline of parallel execution, with each processor handling a distinct image detection task. The parallel portion of the program completes in parallel with the time it takes for a single image to be processed. Moving on to understand parallel computer architecture, Flynn's taxonomy, proposed in 1966, provides a systematic framework for classifying parallel computer based on the two independent dimensions, instruction stream and data stream. The term stream refers to a sequence or flow of either instructions or data operated on by the computer. In the complete cycle of instruction execution, A flow of instruction from main memory to the CPU is established. This flow of instruction is called instruction stream. Similarly, there is a flow of operands between processor and memory bidirectionally. This flow of operands is called data stream, and these two types of stream are shown in this figure. Now let's explore the four classifications defined by Flynn. The first classification is single instruction or single data SISD. In SISD architectures, only one instruction stream and one data stream are processed at a time. This type of architecture is synonym with traditional serial computer or non-parallel computer. The key characteristic of this as ISD is only one instruction stream is executed per clock cycle. Only one data stream is used as input per clock cycle, and instructions are executed in a predetermined order or deterministic execution. A great example is the older generation mainframes, mini computers, and workstation, and single process or core PC. And it is shown this one, the image, UNIVAC 1 and IBM 3360. The second classification is single instruction multiple data SIMD. In SIMD architecture, all processing units execute the same instruction simultaneously, but each unit can operate on a different data element. This type of architecture is well suited for specialized problems with a high degree of regularity, such as graphics and image processing. The key characteristic of this SIMD is all processing units execute the same instruction at any given clock cycle. Each processing unit operates on a different data element, and it is synchronous execution which processing unit operate in synchronization. An example for this one is process array and vector pipelines, which is this thinking machines and Cray XMP. Moving to the third classification, multiple instruction single data MISD. In MISD architectures, each processing unit operates on a data independently via separate instruction stream, while a single data stream is fed into multiple processing units. However, few actual examples of MISD computer have ever existed and its practical applications are limited. The key characteristic of this is each processing unit operates on the data via separate instruction stream, and a single data stream is fed into multiple processing units. And a potential application for this one is multiple frequency filtering operation can on a single signal stream, or multiple cryptography algorithms attempting to crack a single coded message. Now, for the last and final classification is the multiple instruction, multiple data, or MIMD. In MIMD architecture, every processor may execute a different instruction stream and work with a different data stream. This type of architecture is the most common in modern parallel computing, including supercomputers, parallel cluster, and multi-core PCs. The key characteristic of this one, each processor may execute a different instruction stream, and each processor may work with different data stream. Now for the execution variability, it can be synchronous or asynchronous, deterministic or non-deterministic. A good example for this one is the most current supercomputers, network parallel computer cluster, multiprocessor SMP computers, and multi-core PCs. Thin taxonomy offers a valuable framework for classifying parallel computer architectures based on the instruction and data stream characteristic. By understanding this classification, we gain insight into diverse landscape of parallel computing and its application across various domains. Now, let's delve into diverse landscape of parallelism. There are three types of parallelism. The first one is data parallelism. Data parallelism refer to a parallel computing approach where the same operation is applied to multiple data points simultaneously. In data parallelism, the workload is divided by distributing data across processing units, and each processing unit operates independently on its subset of data, performing the same computation on each data point concurrently. Video encoding is a classic example of data parallelism. Each frame of a video can be processed independently by separate computing units. This approach allows for simultaneous encoding of multiple frames, significantly reducing the overall processing time. Now, moving on, task parallelism. Task parallelism involves dividing a computation into dependent tasks that can be executed concurrently. In task parallelism, different tasks are identified within a computation, and each task is executed separately and concurrently by multiple processing units. This approach maximizes resource utilization and reduces overall processing time. In a web server application, incoming requests from clients can be handled concurrently by multiple server threads. Each thread processes a different request independently, allowing the server to serve multiple clients simultaneously without delay. Last but not the least, pipeline parallelism. Pipeline parallelism organizes tasks as a series of interconnected stages, with each stage performing a specific operation on data. In pipeline parallelism, data flows through a series of stages, with each stage just completing a specific operation on the data before passing it to the next station. Multiple stages operate simultaneously, allowing for efficient processing of data and reducing idle time between tasks. A manufacturing assembly line is an example of pipeline parallelism. Each station is the assembly line perform a specific task on the product as it moves along the line. For instance, one station may weld components while another paints the products. As each station operates on different products simultaneously, the overall production process becomes more efficient. Let's explore the diverse memory architecture utilized in parallel computing. Shared memory systems allow all processors to access a common global address space, facilitating fast data sharing between tasks. This system can be classified into two, which is the uniform memory access and non-uniform memory access architecture. The Uniform Memory Access, or UMA, it is represented by symmetric multiprocessor machines. UMA systems feature identically processor with equal access time to memory. Cache coherence ensure consistency across processors. And the non-uniform memory access, or the NUMA, often created by linking SMPs. NUMA system offer direct memory access across processor but with varying access time. Cache coherence may be maintained in CC and UMA architectures. For example, imagine a SMP machines commonly found in modern multi-core computers. In an SMP system, multiple CPU cores share access to the same physical memory. Each core can execute tasks independently, and change made to memory location by one core are immediately visible to all other core. For instance, in a scientific simulation running on an SMP machine, multiple CPU cores can simultaneously access and update shared data structures, representing simultaneous variables, enabling efficient parallel computation. Next is distributed memory. Distributed memory system feature processors with their own local memory, requiring a communication network for inter-processor memory access. Each processor operation independently, and data communication between processor is explicitly defined by the programmer. A good an advantage for this one is scalability with the number of processor, rapid access to local memory, and cost effectiveness with commodity processor and networking. The disadvantage for this is the programmer responsibility for data communication and synchronization, challenges in mapping global memory-based data structures. An example, consider a cluster of network computers, each equipped with its own local memory and processing unit. In this distributed memory system, each computer operates independently and has its own address space, meaning memory address in one computer do not map to memory in another computer. To perform tasks that require data from other computers, implicit communication and data transfer protocols are implemented by the programmer. For instance, in a distributed computing environment, tasks such as data processing, image rendering, or scientific simulation are divided among multiple nodes in the cluster, with communication mechanisms facilitating data exchange between nodes are needed. Now we have hybrid distributed shared memory. Hybrid architecture combines shared and distributed memory components, often seen in high performance computing systems. The advantage and disadvantage for this one is inherit both advantage and disadvantage from shared and distributed memory architecture. It increases scalability is a key advantage, while increased programmer complexity remain a challenges. Let's consider a high performance computing cluster consisting of interconnected nodes. Each comprise multiple CPU cores and GPUs. In this hybrid architecture, each node operates as a shared memory system with CPU cores and GPUs accessing shared memory resources within the node. However, communication between nodes relies on a distributed memory network, allowing data exchange between different nodes in the cluster. For instance, in a deep learning application running on a HPC cluster, the training process may involve parallel computation on GPU cores within each node, while communication between nodes facilitating model synchronization and parameter updated across the cluster. This illustrates the diverse way in which memory architecture are structured in parallel computing environment, showcasing their representative advantage and application. Now, let's explore the crucial concept of granularity in parallel computing. In parallel computing, granularity refers to the qualitative measure of the ratio of computation to communication, or periods of computation are typically interspreaded with periods of communication, often separated by synchronization events. It can be classified into two main categories: fine-grained parallelism and coarse-grained parallelism. Fine-grained parallelism involves relatively small amount of computational work being performed between communication events, resulting in a low computation to communication ratio. Facilitating load balance by distributed smaller tasks evenly across processing units. It implies high communication overhead and less opportunity for perform enhancement. And if granularity is too fine, the overhead required for communication and synchronization between tasks may exceed for the computation time. For the coarse-grained parallelism, it entails relatively large amount of computational work being executed between communication or synchronization events, leading to high computational to computation ratio. This provides more significant opportunity for performance enhancement due to longer computational periods, but in harder to efficient balance the workload across processing units. You might ask which is the best one. So the most efficient granularity depends on the algorithm and it the hardest in the hardware environment. In many cases, coarse grained parallelism is preferred due to the high overhead associated with communications and synchronization relative to execution speed. However, fine-grained parallelism can mitigate overhead related to load imbalance in certain scenarios. This understanding of granularity provides insight into optimizing parallel algorithm for improved performance and efficiency in diverse computing environments. Now, let's witness parallel computing in action. Parallel computing enables astronomers to simulate the behavior of celestial bodies, analyze vast data set of astronomical observations, and predict phenomena such as supernova and gravitational waves. Another example and use cases of parallel computing is the agriculture predictions. This aids in analyzing agricultural data, including weather patterns, soil composition, and crop yields, which to optimize farming practices. It is improve crop productivity and mitigate risks related to climate change. Another example and use cases is in the film and entertainment industry. Parallel computer accelerate tasks such as 3D and rendering, video encoding, and visual effects rendering, allowing filmmakers to create stunning and immersive cinematic experience. In conclusion, parallel computing is not merely a technological advancement. It is a catalyst for innovation and discovery. By embracing parallelism, we unlock unprecedented computational capabilities, revolutionizing industries and advancing scientific frontiers. Thank you for joining me today for this in depth parallelism computing.